So it is a pleasure to welcome Dan D'Orazio. Dan got his PhD at Columbia with Zoltan Hyman, then was an Einstein Fellow at Harvard, and was an assistant professor at the Niels Bohr Institute at Copenhagen, and has recently moved to Space Telescope Institute, where he's an assistant astronomer. And he's going to continue our tradition of binary black hole talks. Thanks, Dan. Take it away.
Yeah, thanks so much, Andrew, and everyone so far for inviting me to NYU. Like Andrew said, I did my PhD at Columbia, and it's actually been quite a while since I've been back. So now that I'm in the neighborhood again, I hope the talk goes well. Maybe we'll see.
We'll invite you back. That's good.
But yeah, so today I'm going to talk about supermassive black hole binaries, and specifically, the meat of it is going to be about their interactions with gas disks, circumbinary disks. And so here are some images of that interaction. Some of them real. Actually, all of them are real. Some of them are real on a computer, though. Maybe you can tell the difference which is which. And so what I want to do today is go through how this interaction of a supermassive black hole and an accretion disk is important for kind of multi-messenger astrophysics. And I'm going to spend some time going through that bigger motivation.
The bottom is real?
That's for you to we can discuss afterwards.
No, but seriously.
But seriously, these are all my observations of, that's a binary.
So this is radio, right?
This is radio, yeah. And that's a triple system, but yeah. And that'll come up again. All right, so I'd like to start with this. Right, so when you take an Astronomy 101 class or open up Rybickian Lightman, you see the electromagnetic spectrum, electromagnetic sky, right? Everything that from radio to visible to X-rays and gamma rays and what physical sources create them and how we detect them. This, of course, is the analog for gravitational waves, the gravitational wave sky, all the way from very low frequency gravitational waves sourced at the Big Bang up to gravitational waves with hundreds to thousands of hertz. And these gravitational waves, as you probably know, are the ones that were famously detected about 10 years ago now by LIGO, Virgo, Kagra collaboration, right? So these gravitational waves at this high frequency end of the gravitational wave sky are from the mergers of stellar mass black holes, binary neutron stars, and I mean it's hard to overstate the kind of importance this has been to creating a new field of gravitational wave astrophysics and physics. And right now we have hundreds of these merger events, and it's opened up a whole field of trying to understand where they came from, to trace the astrophysical environments that bring these systems together. So this will continue to be exciting now and in decades to come. But what I'm going to focus on today, that I'm most excited about, is the future of the low frequency gravitational wave sky. So there we have two main detectors, or detector types. The first one here, if you go to lower frequencies in the millihertz, is LISA, the laser interferometry space antenna, which will be an interferometer with 2.5 million kilometer arms in space. Let's go to lower frequencies. How do we detect even lower frequencies? So nanohertz can be detected with these pulsar timing arrays, which are detectors the size of the galaxy, where you have a bunch of clocks set out through the galaxy manifested as millisecond pulsars, and you can detect these really long wavelength gravitational waves coming together by timing those clocks. Okay, those are the detectors. Of course, the main source, well, I hope there are many different sources that are even beyond what we thought of so far, but the main source in these millihertz to nanohertz regime are the supermassive black hole binaries. For LISA, this is the mergers of the, say, 10 to the 5, 10 to the 7 solar mass binaries, the mergers and late in spirals. Whereas for the pulsar timing arrays, this is kind of the late in spiral before merger of the really biggest black hole binaries that exist, the 10 to the 9, 10 to the 10 solar mass supermassive black hole binaries. And so I'm saying this is the exciting future. Future is pretty much now with the pulsar timing array. It's starting now. There is strong evidence for a gravitational wave background in this nanohertz regime that was announced in 2023. And for LISA, this is no longer just an idea, but a mission that has been adopted by the European Space Agency with a planned launch in the mid-2030s. All right. So, supermassive black hole binaries, let's now get to the astrophysics. Where are these coming from? And so let me go through quickly this kind of three-step cartoon. And let's get to a little bit of astrophysics here. So there are supermassive black holes in the centers of galaxies, right? We have evidence for that, and we have evidence that galaxies merge, right? After a galaxy merger, the idea is that those two black holes can be dragged down to the center of the new galaxy, where they can form a binary black hole. If that binary black hole gets close enough, we can get excited and skip all the way to step 3. Step 3 is that when they are close enough, they'll emit gravitational waves so vigorously that angular momentum energy is carried away. They emerge, and we see that in LISA, or the pulsar timing arrays, right? But of course, we skipped a number. Step 2 is how do they get close enough, right? This has been talked about for over 40 years as kind of the final parsec problem. How do you get these two binary black holes to within this separation? Well, they'll emit gravitational waves and merge in the age of the universe. And I think if you talk to different people, they might say this isn't a problem anymore, mainly because there are ways you can think of getting them close enough together. But the way I like to think about this problem is not that we can come up with a theoretical way to merge them, but we would solve the problem, we'd figure out how this is happening. So to understand how this is happening,
Sorry, and the separation in that picture would be about a kiloparsec
I'm
or
going to
something?
go through this in a much more.
So you will tell us.
I will tell you.
Okay.
Yeah. But I want to get the cartoon picture first, and but yeah, below a parsec. But the idea to solve this problem is to model this interaction of the binary with its environment, because it has to have some environmental interaction to bring it from these large scales to these small scales. Some way to get rid of angular momentum that's not gravitational waves. And the main thing we're going to focus on here is interaction with gas, a gas disk. Of course, stars are important. We can talk about them, but I'll focus mostly on the gas today. So that brings me to the kind of approach I have to trying to solve this bigger picture problem. We have this environmental interaction of a binary with gas. If we can model this sufficiently, we can predict how the orbit will change over time, and we can use that to make population predictions for the supermassive black hole binary population. Okay, population predictions are something, but interaction of gas with black holes is also famous for making them very bright, right? So this should also give us a way to look for these systems in the universe with electromagnetic signatures, also gravitational wave signatures, and take a census. So by modeling this interaction, we hope to do both of these things, and when you have population predictions and measurements, census of the population, that's demography. That's how you start learning about the system as a whole and how it evolves over time. That's the high-level picture of the whole plan here. All right. But as I said, I want us all to kind of be on the same page here, the same picture in our mind for when this is happening, when these disks are important. So I thought it'd be really fun, or at least fun for me, to go through kind of a sense of scale of the stages of the evolution of a supermassive black hole binary. And the whole idea here is going to be to give you an idea of when specifically is the gas disk interaction important, because accretion, angular momentum exists, so accretion often happens through a disk-like process. Although there are other ways that gas can be important in this problem. So I'm going to do this with the following plot, which I'm going to explain. But there's lots of lines and shaded regions here. I'm going to add a lot more. So this is a plot of what I call the space of binary orbits. So on the y-axis is orbital period, rest frame orbital period of a binary. And on the x-axis is the total mass of that binary. So 10 to the 5 to 10 to the 10, these are the supermassive masses. And the lines I've drawn down here are just to give you an idea of the physical separations in parsecs. And importantly, if it was only gravitational waves bringing these together, this is how long it would take for them to merge. So this line is important because it's saying a binary somewhere on this line would take the age of the universe to merge from gravitational waves alone. A year here. That gray dash line is the first thing I want to draw on here. First I want to say what is a binary versus a dual. Because we do see, this is a real image, right? X-ray on top of optical. We do see dual AGN, two accreting supermassive black holes that are hundreds to thousands of parsecs apart. But at some point, you can define, well, when do we call that a binary that is bound compared to its environment? And this is just one way of defining when we can call this a binary compared to, say, some surrounding cluster of stars. So this is our binary line. Below this, we have a binary. now I want to get back to the gas. So on large scales, we can draw a limit from the idea of self-gravitating disk. So essentially there is a maximum radius. If you have some solution for accretion disk, there is a maximum radius where that disk will become gravitationally unstable, collapse under its own weight. And we can essentially write that down from some standard disk model. And what I've shaded here is that region. And the point is that this corresponds to a maximum binary separation for which you can have a non-self-gravitating disk surrounded.
Why disks appeared all of a sudden? Suppose there is no disk, there is just a binary and some spherical mass around it. You slipped your disk without any comment.
Well, my only comment was that a small amount of angular momentum I expect to turn into a disk, but we could have a discussion about different
But
types
you are
of
just
accre-
considering binaries surrounded by a disk, period.
Yeah, and getting a feeling right now for where
Whether or
that
not
space-
other systems are interesting, you are not discussing.
Yes, yeah, at the
Okay.
moment, right. So you could probably draw a few other features on here to consider gas dynamical friction when that is important, or some type of Bondi accretion. Right, yeah, right now I'm
I
considering...
just want to understand the rules of the games. Your game is disks.
Yeah, game is disk right now, angular momentum. All right? But that is some type of large-scale classification for the disks, self-gravitation. On the small scale, there is a point, a line I want to draw here that I'll call disk decoupling. And this is essentially when if you do have this gas disk surrounding your binary, the binary will start to decay due to gravitational waves faster than the disk can keep up at some point. And disk keeping up means there's some viscous time for the disk compared to a gravitational wave merger time. And so below this line, the disk doesn't strongly couple to the binary. And of course, this will depend on a lot of things like the thickness of your disk, or essentially the temperature, how important pressure is, or the viscosity in the disk. But this just gives us a cartoon kind of schematic of this lower limit. So around 100 Rg, you expect maybe the binary isn't as importantly affected by the disk. And I'm just now going to color in between what I'm going to call the realm of circumbinary disks in orange here. So where you have a binary down to roughly where it decouples, which again, this can move around quite a bit.
So for the most massive black holes, you don't expect any imaging where
So
many disks are
it's
around.
a very interesting point. So for the most massive black holes, it's hard to fit a non-self-gravitating disk around them. You can again move this line a little bit by changing the accretion rate and some parameters of thermodynamics, which I'll mention, which might tell you it's hard to grow black holes very large through accretion if you were thinking about that. But the first thing to notice, for my point in the very early motivation, this realm of circumbinary disks straddles the Hubble time. So as many people have pointed out, gas can be very important for bringing you past this final parsec, which isn't necessarily a parsec. You can see for this set of parameters, it depends on the mass, and it ranges from a parsec down to almost, thousandth of a parsec. All right, that's the first observation. Secondly, you'll see that this straddles a line between, as I mentioned before, self-gravitating and non-self-gravitating disks. So it could be that these disks fragment and you don't have standard accretion, or if, depending on thermodynamics, these could just accrete as a kind of self-gravitating disks where you can have angular momentum transport just from spiral waves from self-gravity itself. But the point is there is a seemingly kind of fundamental difference of the accretion flow for these more massive systems. And I'm going to draw a line here, which I hope to say more about in the end. And this is more schematic, and I'm not going to spend a whole lot of time describing why. But I'm going to draw a line here at about 10 to the 3 gravitational radii, where below this, so in accretion, one of the important pieces, of course, there's mass conservation, angular momentum conservation are important to accretion. One is energy conservation. And your main source of heating for an accretion disk around a single black hole is viscous dissipation. And at some point, that heating rate needs to be balanced by cooling. So if you have an optically thick disk, that cooling is from black body radiation. But at some point, you cannot keep up with the cooling, and your disk disk can transform into something that is radiatively efficient, black body cooling keeping it thin up here, to something that's hot and puffy. And this is also a fundamentally different type of accretion flow, which again I hope to mention at the end here when we talk about electronic signatures of these systems. But you see that it's actually these kind of more compact systems and higher mass systems too that spend more time here where this is important. Okay, and finally I'm going to draw on here for perspective where the gravitational wave detector bands are roughly. So LISA, you'll see here, for the smaller mass, as I said, and the PTA is up here even before merger for the much more massive systems. And so you can get a feeling here for the pulsar timing arrays. You actually have importance of the circumbinary disk in band, and you can see that it'll be sculpted by this combination of either self-gravitating flows or these hot, puffy flows, which will keep it from becoming self-gravitating. Whereas the LISA band is sculpted by these non-self-gravitating flows, accretion flows. All right. So I just want why this is important, just a real quick point here about this, is that, as I said, if gas disks are what driving these binaries across this line towards merger, then that's going to be important for predicting merger rates and also the properties of the systems as they come into the band. So if they can create some eccentricity or change the spins, those are the kind of properties you want to predict for the systems that will merge in LISA. And can also, as you see, there is some overlap here, and that overlap can be larger depending on the disk parameters, could affect the waveform in band. So dephase the waveform, which I'm kind of showing a picture of right here due to gas interactions, which would help you understand if gas is actually bringing these systems to merger. Okay, and then for the pulsar timing arrays, this is important because, again, as I mentioned, the gas can be affecting the binary as it's emitting gravitational waves in the pulsar timing band. And one of the main observational kind of products you get out of the pulsar timing array is something called the spectrum or the gravitational wave background. So you have this gravitational wave background, which is noise from a bunch of inspiraling binaries, and depending on how quickly they move through their separations, they'll emit more or less power in each of these frequency bands. So this is kind of the strength of the spectrum, the characteristic strain at different frequencies. And these violins are data from the Nanograv consortium. And these lines are two different types. This line is this kind of power law, which is an f to the minus 2/3, is what you get if it was purely gravitational wave emission. And this one that turns over is what happens if you have the gas or the environment changing the orbit as it inspirals. So this now can also give you some hints, some ideas of how these systems come together. So this is the importance for the pulsar timing array bands. All right. And finally, it's accreting here, as I said. So there should be room throughout this section of this space of binary orbits where we can find electromagnetic signatures, binary accretion. But before I get to possible electromagnetic signatures, the first part of the talk, I want to talk about more of the orbital dynamics. How does the gas disk actually move a binary through this space? And I want to focus on a few lessons we've learned from modeling these circumbinary disks. So, part 2 now, we jump into binary disk dynamics. So, what do we start with? A binary with semi-major axis A, eccentricity E, total mass M, and a mass ratio Q. And if we understand how this system evolves in the presence of a gas disk, well, we solve some system of equations for a fluid at some approximation in the potential of this binary. So if you wanted to do it including most of the things that physics that we think should be there, you should solve some type of magneto-hydrodynamical equations and then also the equations for radiation transport in the gravitational potential of the binary, which could or could not include relativistic effects or full GR. This is the system at kind of the full physics. I mean, there's also physics I'm even leaving out here, of course. But I only bring this all up because what I'm going to show you today is what I would call kind of the simplest non-trivial version of this problem, where we keep the dimensionality in 2 dimensions and look at a height-integrated hydrodynamic equation, viscous hydrodynamics.
Because
So
the full problem is not even solved for a single black hole.
Exactly. So that's what I should have said, is that this is a problem we're still working on for a single black hole. And so if we want to focus and learn something about the binary problem, I'm looking at this problem because one of the important things here that's different than a single black hole is the orbit of the binary, right? We have new parameters from the single black hole picture. We have orbital elements. An important thing is how do the gravitational dynamics of the orbit interact with this binary? And we can get that from a two-dimensional hydrodynamic approach. So this is what we're doing. Solving highly integrated 2D, viscous hydrodynamics. And even further, for most of this talk, we'll assume a locally isothermal equation of state. So we're not solving an energy equation, you're just prescribing a temperature profile in the disk.
What does it mean locally isothermal?
Meaning that I can have a radial or even spatially
You prescribe
changing.
temperature?
Yeah,
By hand.
by hand, yeah.
And you feel okay about it?
No, but here's the thing, and I think that's what I hope to get to, is that there's a lesson you can learn from this that tells you when and why to relax it, and I hope I can get that across, so, yeah. So, this is the problem we're solving for most of this talk.
Sorry, very nice question. What about the spins? Are not important for accretion? Suppose one of them is
Yeah.
highly spinning, right? The accretion actually being
Yes.
co-rotating or counter-rotating is like big.
So, the spins, yes, I think they will be an important part of this problem. Right now, because I'm not treating general relativity, I'm treating these as simple sinks in the problem where the spin doesn't come in at that level of approximation. Or you can even treat them as a pseudo potential, like a Paczynski potential, but for now they're just sinks without spin.
Mhm.
Okay, so let me ask a question on the other point then, since we've had 1 and 3. For 2, what
Yeah.
this I mean I guess you're probably gonna say this, but alpha viscosity, are you varying? I mean that's a pretty big assumption. Are you gonna explore different viscosity parameters, or can you just say a bit more on the viscosity?
Yeah, so we're choosing an alpha viscosity, which if you're not going to do that, then you have to include some other angular momentum transport, which means you resolve magneto-rotational instability, or you have self-gravitating disks that can transport angular momentum, or some other way. But right now, because we're not including magnetic fields or self-gravity, we're prescribing an alpha prescription, and we're going to change essentially the alpha constant,
Alpha,
or
exactly.
the coefficient of
Cool.
of kinetic viscosity.
Great, thank you.
Mhm. And I can show you movies where this is done with MHD later. But
Sick.
Okay.
We were talking about MRI earlier, so that
Okay.
good.
All right. These choices actually simplify this problem quite a bit in the sense that we have 2 disk parameters, viscosity parameter, and a scale height, which tells you how thin it is and how important pressure is. And really only 2 important binary parameters now because we can scale out the mass and the semi-major axis. So it's just really the eccentricity and the mass ratio which change the dynamics of this problem. Okay, so what do we find? I want to start actually a little ways back from today. So you can do this problem. I said the mass ratio is one of the important parameters for dynamics. You can do this problem for different mass ratios, and a natural place to start is for a mass ratio that's very small, which means you can solve this problem perturbatively with linear perturbation theory, which was done in the late 70s and early 80s. Namely, this is one of the famous papers doing this. And the result, without going too much into it, is that this is the big guy at the center, this is a little guy with a millionth of the mass of that guy, and as it orbits around, it creates perturbations in the disk, these spiral density waves. And those spiral density waves carry away angular momentum and can cause this system to migrate inwards. Right? So this is often called type 1 migration in the planetary literature. But we can increase the mass ratio because we're working towards equal masses. If you increase this, say to 1 to 100, then these spiral density waves become nonlinear very quickly, and they shock very quickly right next to this orbiter and create a low density gap in this system. And these systems also cause the binary to inspiral. and this kind of rate of inspiral.
This is all in a rotating frame, correct?
This is in a rotating frame, and this is too. You just can't see the movie; it's so steady. It's not a movie; it's a picture. But, this is actually one of Paul Duffel's simulations, who is a student here, and this is one of mine for demonstrating purposes. Rotating frame. Open a gap because of shocks in the slightly nonlinear regime, and you push the binary inwards in what's called type 2 migration. That brings us up to equal mass ratios. Now the system becomes highly nonlinear. This binary carves a very low density cap.
Why are you not in a
cavity.
rotating frame here?
That's a good question. I liked how it looked better, actually. But,
But looks are deceptive.
they are. Yeah, you can do this in a rotating frame.
It's hard to get the whole CBD in the rotating frame because it's large.
Yeah, that's true. And there's also really only one rotational frequency here. Here there's a few new frequencies, actually. But yeah, because I'll show you in a second what you can see. But now you've carved this low density cavity, and the question is what happens here? Okay?
Dan, do you
Yeah.
expect eccentric cavities even for like a circular binary?
This is a binary on a circular orbit,
Okay, and still
which
you,
is one of the surprises of this problem.
Yeah.
You start with a symmetric system.
Mhm.
And, well, I wanted to say something about just this vanilla case, and this vanilla case is circular, equal mass, and I'll show you in a bit, a relatively thick disk, an aspect ratio of 0.1, but I'll get into that. And so what are the kind of key features of this solution for equal mass? So the first, like I said, you carve this low density cavity, black, and it becomes strongly asymmetric due to this binary pulling streams off of this edge of this cavity wall and flinging them into the other side, where these streams pile up and you get this overdensity, which actually orbits around the cavity wall. But the interesting thing about these streams, so some of the first kind of looks at this problem, thinking about it in 1D, thought that these systems wouldn't accrete at all because you have some torque propeller from the binary. That torque does indeed clear this cavity. Actually, if you just looked at the restricted three-body problem, you would see that there are not stable orbits here. That's essentially why there's nothing there. But it doesn't stop accretion. And actually, what you find is that if you run these systems long enough, so you can find a steady state, where the accretion rate that you set way out here, and this simulation is set up with a domain that's way over here. We're just looking at the inner part of it.
Is there a back reaction here? Like, is there finite mass in a disk which can influence the orbit or not?
Yeah, so zero mass disk. the
So
orbit is
zero mass.
fixed.
So the orbit actually is perfectly circular. It is not evolving.
It's perfectly circular, yes. This has been done for a live binary. The answer is pretty much the same. It's also been done for 3D MHD. The picture is pretty much the same. So there's something very interesting, very robust about the gravitational dynamics here, as long as you have a disk.
No, because
Yeah.
maybe it's totally off the maybe not, because I thought that, for example, Magda is studying how eccentricity evolves or whatever, and other people too. You are not doing it here.
That's
right?
yeah, I'm gonna actually talk
You
about
will jump to it
about
later.
all of these things, actually have some of those things. We'll see, yeah, I'll talk about
No,
eccentricity.
but,
and
but
thickness,
here
yeah.
the mass of the disk is zero.
Yeah, well, yeah, for the rest of this talk, the mass of the disk will be 0. Also in Magda simulations, the mass of the disk is 0.
She just computes E dot and stuff like that.
Yeah.
Okay.
Which is the next slide, so we don't have to do it. But, yeah, but I think it is an important point to realize that you can find a steady state where the accretion rate here, that's set out here by viscosity, can match the accretion rate onto these black holes if you go for long enough. And same for global angular momentum in the disk. These two, you can find steady state solutions. And those steady state solutions are completely mediated by how much material you're pulling off this cavity wall in these streams, which then adds to these mini disks with the rest of it.
Sorry, I don't understand. Is
Yep.
not M dot dictated by the boundary conditions at infinity? Whatever is happening at infinity is pushing a certain M dot onto your binary. Your binary will have to swallow it.
Exactly.
True or false?
True.
So M dot and J dot are set by infinity, or only M dot?
No,
because
because,
normally only M dot is set by infinity.
Yes. M dot is set by infinity. J dot is set by a coupling here.
Okay.
Even in the single black hole case, it's set by the coupling in the boundary layer. Here, that boundary layer is much more complicated.
So
It's
M
actually
dot
set-
is a parameter, J dot is the outcome.
Yes.
Okay.
Yes. Exactly. All right. So, the point is now to calculate what happens to the orbital evolution. And to do that, we're going to do exactly what Andre said. The simplest way is to use the fact that the binary on its own has conserved energy and angular momentum, specific energy epsilon, angular momentum L, and compute how these change in time, how the orbital parameters change in time. So A dot, time rate of change of the binary semi-major axis, or E dot, time rate of change of the eccentricity, due to L dot as a torque, E dot as a power on the binary from the gas. You get those from solving these equations over time and computing those from the hydrodynamical simulations. Just so we're all on the same page of what I'm going to tell you next, how we compute the orbital evolution is mostly this brute force approach. You can also use conservation laws to understand if you're correct, like that conserved angular momentum current, but this is the basic approach. And so I wanted to first start here saying that, from linear theory and, simple estimates of gas hung onto the binary, the picture was pretty much that you would expect the binary to decay, right? We saw type 1, type 2 migration, the binary is decaying. You can also ask if you throw some gas onto a binary and it expels it, it should lose angular momentum at some rate proportional to the accretion rate. But detailed calculations like I just kind of went over have shown that in some cases these orbits expand. And I think Magda gave a good talk on that yesterday, I heard. But this was somewhat of a surprise to understand why this was happening. And I'm not going to go into detail the reason why this happens, because I want to get to some other pieces. But what we did 3 years ago now, was try and bring people together that are simulating this problem and understand if we can all agree on this. And so we had a KATP conference at Santa Barbara, where we had about maybe 10 or 12 people with around 10 different codes try and set up the same exact problem and see if we all agreed that the binary could expand. And this is, as some of you may know if you've done code comparisons, a bit of a social experiment as well as a numerical experiment. But in the end, it was very successful. So Magda was part of this. Yeah, there was a number of people that were part of this. And we did find agreement in the end that in this specific set of parameters, the vanilla case I was just showing you the movie of, there is angular momentum delivered to the binary, and it wants to expand. I think that is settled.
So you solved the last parsec problem. They don't merge.
In some cases, orbits expand, but it's a very non-trivial dependence on the parameters of the problem. Even in this case where I said all we have is viscosity, disk thickness, and binary parameters, you find that if you change the viscosity and the disk thickness, you get different answers. I'm not going to talk about these plots, I'm just giving you an idea. You find that if you change the thermodynamics, so get rid of the isothermal picture in different ways, the answer changes. You change mass ratio, eccentricity, the answer changes. So what I want to do is go into two different cases here, two different stories about two sets of parameters that we've looked at and what we've learned about this problem from those sets of parameters. And I'm going to start with eccentricity. So, this is this movie we have been looking at before. This is actually just E equals 0. But this one might be a little, no, this is small e, but it's very similar to that movie we were just looking at before. If you increase now the eccentricity of the binary, I'm just going to let you stare at these hypnotizing movies for a minute, you get these different solutions, and we're just going to use those solutions to compute A dot and E dot. And so with Paul Duffel, a little while ago, we did a numerical experiment where, like I said, we're fixing the binary orbit. What we do is start a binary in a circular orbit, get the solution we just had, and adiabatically, very, very slowly increase the eccentricity of the orbit. And as we do that, we continuously measure what A dot and E dot, precession rate, and everything, M dot on the binary is. And so I just want to explain what we find with something not quite as beautiful as these movies. this colorful plot here. So what do I have? I have two different colored curves. The purple one is telling us A dot, how the semi-major axis will change. So above the line, it's expanding. Below the line, the binary is decaying. The orange one is probably the more important one to look at here. That's E dot. So below the black line, the binary is becoming more circular. Above it, it's becoming more eccentric. And so what's the lesson? What do we learn from this plot? Well, first you can see this one point in parameter space we already looked at. The binary doesn't want to change its eccentricity, but it wants to expand. The purple line is above 0. This is that one part of parameter space here for a circular orbit. All right. But now you can see that as we move through this space, there is this really sharp transition here and here at eccentricities of about 0.2 and 0.4. What we observe in the solutions for the density again here is that interesting, right at these transitions, the binary, this asymmetry in the disk kind of pops into a much more symmetric kind of m=2 state right at those transitions, very, very drastically. Here's another, oops, sorry. Yeah. Okay, and then as we go to higher eccentricities up here, it seems to pop back into a much more asymmetric state. All right, so what can we learn from this picture? Well, you can think of any binary system that you want to start with at some initial condition, E, starting anywhere in the space. What would happen to it? Well, if we start at very low eccentricity, say below this 0.1 or so, then the binary wants to circularize, so it just moves back here. So that's a fixed point.
Sorry, can you say a few more words about the nature of these phase transitions? It looks like you have almost a phase transition at 0.2 and 0.4.
Yeah.
And both lines, in fact, cross 0 at the same point.
Yeah.
Right? Going in opposite directions. So what exactly happens at 0.2 and point? It looks like, isn't it what you said? It becomes perfectly Z2 symmetric, or whatever is your terminology.
I said m=2, but the same idea, some kind of symmetry around the center of mass for this equal mass system.
So it becomes like pi/2 rotational, not pi/2, whatever, rotationally invariant by 180 degrees rotation or something, or what?
Yeah, so you have two kind of equal streams coming in so that there isn't this eccentricity to the cavity. And, well, we're actually still trying to understand why exactly this happens, but the intriguing thing is there is this state change which has a huge effect on the orbital.
But is it true or is it false? Between 0.2 and 0.4, you are perfectly 180 degrees rotation invariant.
I wouldn't say perfect, but it's much closer to that than this.
Than before or after.
Yes, exactly. And it seems to align right with these.
The emergence of this
yes,
symmetry.
so it seems like
this is what you called M2 symmetry, right?
I did. Yeah.
Okay.
Yeah. Mm-hmm. So that to me is intriguing.
It's like, it looks like odd harmonics like disappear,
yes,
almost.
Exactly. Is you can do a mode analysis of just the density profile, the structure, and try and see which are the most important symmetries still there, and it's mostly this 2, whatever equals 2.
And you guys have zero understanding why it happens.
So we've been trying to figure that out exactly, because we can have a good picture of that. Then you might have a reason to understand when you add more physics, when is this going to happen? Because let me just say there's something really important that happens here, which maybe Magda has talked about before because she has worked on this, is that if you pick some initial eccentricity now above this point, right, if it's here, it's going to evolve to this point. It's going to get more and more eccentric till here. If you start here, it goes back. It's a fixed point in the space, right? So you have two fixed points in the space, two attractors. One corresponds to circular out spirals, and the other, as you said, it's interesting that they both A dot and E dot cross 0 here. So there have been other simulations where this isn't exactly, this might be a coincidence at this point, but in all of the simulations that have been done of this, the result is that the binary stays, well, in this case, the binary oscillates around this eccentricity of 0.4, but because there is a lag time between this transition, so from the symmetric to the asymmetric state, there is a time it takes to pop into one versus the other, and the time to go from one direction to the other direction is not symmetric, it actually spends more time decaying than it does expanding. So you end up oscillating around point 4 and decaying. So you have two fixed points, and this other one is an eccentric inspiral. And I will say that this is intriguing. That it has something. It seems to have something to do with this state change. And there have been some. So there has been some work we've been thinking about to try and understand this. We've been looking at with a student, Marcela Gerchik, at kind of linear theory of how you excite eccentricity in a disk from a binary, and seeing if that can explain it. It doesn't seem to be the whole picture. It seems that you have to understand how the streams impart angular momentum to the disk to change its morphology. So right now we're in the middle of an analysis where we're doing this same kind of calculation, but we're cutting more and more of the streams out and comparing that to the linear analysis to try and see if we can come up with some picture of how this is being excited. I mean, to answer your question more, there were some analyses that looked at how different, for the aficionados, eccentric Lindblad resonances could cause this structure, but I'm not convinced that's what's happening. This is really an ongoing kind of puzzle, but it brings up a really important thing to focus on here. By looking at this, least trivial, interesting case, you can see that the dynamics of the inspiral might be tied very much to this transition. So that's the main lesson from this eccentric.
So this
study.
crossover between A dot and E dot, like, is it saying that, like, I always wondered when, if the binary gets to that point, there's neither evolving in eccentricity, neither evolving in similar axis. Is that what the implication of this picture is? Or is it that there is not enough resolution around that point that maybe they are not matching at the same point?
No, I would say the picture here is that like I was saying, at that point, there is actually some. So if you have a system, here's the eccentricity curve, and it's decaying to this point, and so it's getting more and more eccentric, and then it crosses the line, right? It'll overshoot, and as it overshoots, you can see. As it overshoots, it'll expand. But then once the symmetry or the asymmetry pops back in, it goes the other direction and overshoots. And as it overshoots, it decays. But you can see this is a lot more strong than that, and actually the delay time is longer on the one side, so you end up you would decay. And what hasn't happened yet is that we haven't just put a live binary here. We should do that, because what's also happening is the binary is processing. It's eccentric and the disk is processing it. So there's some things to understand further with the dynamics here.
And is it surprising to you that A dot, I think in this setup, because the binary is fixed, so A dot is independent of E, right? The study with Alicia, it's only for circular binaries. So when the binary is eccentric, it will be interesting to see how A dot also depends on that.
Yeah, right. Yeah, I agree.
Dan, presumably these lines are averages.
Yes.
What is the variance like? Like, could you have time periods where you're in this circular out spiral phase where you're actually increasing the eccentricity just from stochasticity?
Yeah, but I'm not sure. Not sure if I would trust the variances from the simulation. I'd have to do a convergence study of what the real variance is, and then when you have a more turbulent flow, it might be different in reality. But it's a good question, because these are averages of a simulation output. It's a good question. But they're not going to bring you anywhere secularly, I don't think. They'll cause variations, which actually Lorenz Wick did a study on how those variations in the torque actually can jiggle your binary around and cause a dephasing of the waveform, even if you're not secularly changing the orbit. So people have looked at these, but for long-term evolution, I don't think it would make a big difference.
Couldn't
We're thinking
couldn't
about-
scatter it up or anything. It would be
Yeah, maybe it could.
I think the rate of change of eccentricity is much slower than the variation of E dot within an orbital period. So
Yeah, we can have you talk more about this. So I think I'm only going to get to the first part of my talk, so I'm going to finish the first part of the talk, but that's good. We can talk about this further. All right, here we were with our lesson, understanding the state changes. Oh yeah, I want to say one more thing about this because I think this is very cool, and it brings up some work that Magda did, where she extended this picture to different mass ratios. What I showed you was for an equal mass binary. It's this cut of this diagram, where we have a kind of phase portrait for binary eccentricity versus mass ratio, and how the binary orbit wants to move in that space from the simulations I just showed you. Here is our fixed point at about eccentricity 0.4. And this is how Magda found that it changes with mass ratios. It actually stays pretty well fixed for reasonable mass ratios. And what I'm showing you a plot of is from a paper by Paul Duffel and his student Alan Murray, where they did a really neat thing, which we looked at some of the KITP program as well. So yeah, that's the equilibrium eccentricity. Remember from the beginning of the talk, the real systems observed by ALMA, circumbinary disks with binary stars. You can look at as many of these as we have orbital parameters for and plot them on here. So there are some systems you wouldn't expect to fall on here, like polar aligned systems, actually where the disk is perpendicular to the binary, or tidally circularized systems. But if you take the systems that match most closely this calculation, where the disk is roughly aligned with the binary, they intriguingly fall pretty close to this equilibrium line. So I think this is worth thinking about why that happens. Part of it might be that which I'm going to get into next, the thickness of the disks we're simulating are much closer to what you might expect in stellar systems. But yeah, it's worth thinking about more. Do we have the physics to have made this prediction correctly, or is there something else that's going on? But it's intriguing.
Dan, how are the masses and orbital parameters inferred?
I don't know. I'm sorry. I can go check. I don't know exactly what they're doing here to get these.
I guess there are like big error bars on each of these crosses.
I mean, I had thought, yeah, there might be bigger error bars on this.
But maybe from lines you do have radial velocities for individual.
Yeah.
Okay, so this is
So
exactly kind of what.
We did a study with Kepler where we looked at the eclipsing binaries, then you can get pretty good, very good measurements. But I'm not sure if these are eclipsing, so I have to check specifically these. And that study also, unpublished, but found some intriguing similarities as well. So, okay, that is it on eccentricity. I want to go through one more story about a different parameter and how that changes things, and that's disk thickness. And I'll say this is a lot of the beginning of what I'm talking about here is work done by Chris Teedy in collaboration with Andrew and others, but I think it's a really compelling story, so I want to go through it. So the disk thickness, everything I showed you so far is for this disks with aspect ratio of 0.1. But there's good reason to believe for black holes that should be a lot thinner. So for stars, I mentioned, that's probably okay. But for black holes, you can look at, you can solve the single disk model and ask what should the thickness be for a system accreting at Eddington for some mass. And you can see that it should be actually a lot thinner, maybe 10 to the minus 2, 10 to the minus 3. So 10 to the minus 2 is reasonable. And if we want to understand what happens for black holes, we should really look at disks that are a lot thinner. So what happens when you do that experiment for disks that are thinner? These are some results from the literature, including by Chris, Sailfishes by Chris and some other groups. So as you make the disk thinner, which is higher Mach number here, but just consider these as thinner disks, you go from this expanding solution, again the case we looked a lot at right here, to systems that are being strongly pushed together. So why is that? So I think a pretty nice explanation of why that happens can be seen from this plot, where we take these density profiles and cut them up into different regions. Essentially, an inner part in red, and then an outer part in yellow, and then an in-between part that's kind of tracing the streams in the cavity in blue. And so now measure the torque from the gas onto the binary in each of those regimes. You can see what happens here is that as you go to thinner disks to the right, the torque from the inner part kind of stays the same, while the torque from the outer part gets a little more negative, pushing it together. But really this blue inner region in the cavity gets much more strongly negative, causing the entire torque to push the binary together. And you can kind of see, this is the much thinner disk. What's happening here? These streams that are threading the cavity are getting much more dense. That's what this kind of white is showing you, is much more dense. Okay, it's an observation. Why is that happening? I think this picture from, again, a paper by Chris and Andrew from very recently, shows really the basic idea of why that's happening. So this is thicker to thinner disks. You can see the mechanism that's mediating this accretion rate steady state that I talked about earlier. This mediation by the streams, it's getting harder and harder for the streams to deliver mass to these mini disks. And so what that means, that if you're going to reach a steady state and measure these torques, that by the time you reach a steady state, you have to have a huge pileup of density in the cavity so that you can feed the disks at the right rate. So out here, you're setting the accretion rate, but these streams are becoming so thin that you're not delivering much mass on each pull. So the density at the cavity edge raises and raises and raises, so that even though you have a small cross-section, you've loaded a lot of mass into it. So this is just a kind of symptom of steady state, and the fact that in these thin disks, these streams become very thin and have a hard time feeding the binary.
So this is kind of equivalent to a statement about the viscous time being very long, so you have to accumulate a lot of mass to match some m dot.
Yes, so whatever the viscous time is, you'll need a number of those to reach steady state.
Yeah, and
Yeah.
and cooler disks have lower viscosity, so
Well, I don't even think it's that here. I think it's really this stream generation mechanism. So if I can, feed something through a hole, this hole is getting smaller and smaller, so I have to make what I feed through there more dense to get the same amount through.
yeah.
And so maybe this plot helps. So these simulations are run to where they do become in steady state. The accretion rate at infinity matches out into the binary, so they're driven to that point. But to get to that point, just look at these solid lines. The density has to increase by orders of magnitude. So I think that picture is relatively clear what's happening here. And you can see then the torque on the binary becomes enormous because you've had to build up the density in the cavity to 1,000 times what it should be for a single black hole.
But you keep the viscosity fixed, right? So when you're changing each of R, that doesn't play into the viscosity prescription, right?
Right, and so I didn't
You
run these
change
simulations,
alpha
but I do know what.
Do you change alpha to compensate for the thin disk?
So,
Or is alpha fixed?
sorry, I believe the accretion rate is, okay, but I can't remember exactly what happens here, but you do reach the same accretion rate and you keep the same viscosity in the disk. It's just thinner. So you adjust alpha to have the same nu.
Yes.
You tell me
It's
wrong, that's what you do.
constant
Yeah.
kinematic
Yeah.
viscosity.
So you keep all the parameters the same except h, and then you evolve it to steady state.
So do you know why the cavity gets larger then? So it looks like the
Yeah.
cavity region kind of gets larger and
I'm not sure if that's true on average, though.
Okay.
I don't think it's larger on average. I think it might even be smaller, but I don't know exactly what it's saying. It's about the same. But I think this leads us to a few interesting conclusions. One of them, just finishing this thought, is that that's well and fine if this is the steady state solution, but to get a buildup of this high, it's not just a viscous time, it's a very long time, and it can be longer than you expect the system to live for. So one thing that you might be taking away from this is that actually these systems could be initial condition dependent. They could depend on how you start feeding the system, not just what the steady state solution is. So one, we've learned that the stream generation seems to be a robust and important factor for how you're applying torques to the binary. And two, that this might take a long time to reach and be initial condition dependent. But I think what all of this leads you to is the fact that we need some more physics here, because we've just set, or these works have just set the thickness of the disk to some value and then a parameter study. But in reality, that thickness is set by other parameters in the system, like the accretion rate, the cooling, the heating. And so I'm going through all this because something that we're working on now is doing this same experiment, but relaxing the isothermal condition, so that we can consistently solve for the thickness of the disk everywhere. Because, you know, one thing I thought looking at this is, yeah, this is the thickness for a single black hole solution. But we have all these streams, and they're causing shocks, and they're heating the thing up, so shouldn't they just puff the thing back up to 0.1 and we're expanding again? This is what we wanted to see, and the simplest next step you can do is now just solve the energy equation with your viscous, binary, compressional heat, shock heating, and add a blackbody cooling function into this. So what you're seeing is now a movie run by, with actually this blackbody cooling, and this is the density. And this is for actually very thin disk, thin enough that you're almost in a consistent state where this is maybe just a little higher than Eddington inferred accretion rate. So this is one of the thinnest disks that has been done this way, and it's really nice because we've put in a single black hole, reproduced Shakura-Senyaev results for the single black hole results, and then just put the binary in here. So this is really nice. It's kind of like the exact extension of the Shakura-Senyaev to binary. All right. Yep. And so doing this, first to just see what happens to the thickness. So I want to show you that result, because these are all preliminary. And so now, if I plot contours not of the density, but of the disk thickness that you see right here, you can kind of see what is happening. So black is very thin, and this orange is very thick. So these streams continue to be pulled off, and they ballistically fly towards the other edge of this cavity. When they shock there, they indeed heat it up and puff up the disk. But as they fall back to where the streams are generated, the disk cools down and becomes even thinner than it was before. And so you can see this here in this plot. This is the Mach number, so very thin, thick, as a function of radius. You can see far away, you reach this dotted dashed line, which is the Shakura-Senyaev solution. But as you come in radius, you get this big dip where it gets thicker. That's just that. And then it goes up to very thin values at the point of stream generation. So this is super interesting. It's doing the opposite of what I might have thought, because all the heating's going on over here, not here. And so what this might mean is that these systems might even be more accretion starved and have faster in spiral than we thought. Or we start need.
Is it some crazy resolution, like 100,000 squared or something? Because you could get this really thin lines,
Yeah,
which in fact are fields.
It had to be very high resolution, run on GPUs with Sailfish code, which Jonathan Zericki and Andrew wrote.
Because these funny lines, they are really fields, right? This is.
Yeah, I'm
this
not
is
sure
a
what
field.
this is actually. That's a good. I don't know what these little aliases are.
Or-
There's a
or
floor.
he could be drawing some funny thing.
I think so. One thing that's happening is there is a numerical floor, which we spend a lot of time in this problem
Okay.
investigating and trying to make sure that our solutions are not dependent on it. And there might be something happening with the temperature floor there, some oscillations.
But the input equations are pure hydro.
Yes. Yes. Yeah.
Sailfish is finite volume, right? It's not zero spectral.
Yes.
Does
Yeah,
kind of
so
look
there's-
like
right, there's no
ringing.
Gibbs ringing out. Yeah. Yeah.
Even to calculate the disk height, there must have been some processing.
That's likely.
Yeah. That's true.
So Dan, would this be a good conclusion to say that the binary will keep shrinking, but it will not accumulate enough accretion mass? So maybe the mass at the parsec scale will not become double of it when it comes to gravitational regime, something like this.
Oh, I see. So you're saying it won't accrete as much.
Yeah.
We could calculate essentially an efficiency here, which is something we want to do. What is the efficiency of accretion as a function of age?
Also the preferential accretion part, whether
Yeah.
the binary will become more equal mass or not or something.
Yeah.
So what's the equation of state here?
This is 5/3, I believe.
Okay, so gas dominated.
Yeah.
Okay.
Yeah, there's no radiation pressure here, which is the next,
Yeah.
which this might lead you towards asking now, what else could break this? Radiation, maybe. Magnetic field pressure, maybe. So those are things that are driving. There's a reason now to start thinking about what physics do we need to understand this better.
You also assume, I guess, constant opacity.
Yes, so you can add, there are some interesting papers that now add more complicated opacity. Even just hydrogen opacity is more complicated than electron scattering or free. So you can
This
do
is
that.
circular, right?
And this is circular.
Okay.
Yeah.
It'd be really interesting to see how the eccentricity evolves.
I agree, and what the spectral energy distribution looks like, which interesting thing we're finding is that it's not necessarily dimmer, even though in the early stages you're not accreting very much. You're still converting the gravitational potential into kinetic, which is then shocking out here. It just changes where it shows up in your SED. So that's really interesting for if we want to look for these systems, which I'm not going to talk about how we look for these systems, but one of the ways is variable accretion and how that signature comes through and how we might find it in time domain surveys. So this is very important for that. And the other next step we're doing here is that, look at all this. Black body, when do you get black body cooling? On a system when you have a high optical depth.
Yeah.
This is not optically, this is optically thin.
Mhm.
So in here, things like bremsstrahlung, synchrotron, inverse Compton are what should be cooling the system. And so we're working on adding this to the picture as well. So not just black body thin disk, but an entire picture where you also have different modes of accretion, like hot disk accretion, and that changes spectral energy distribution, changes dynamics. And so this is the direction we're going from these kind of simple isothermal 2D simulations to try and understand where we need to add what physics is most important. And those are why I told those two stories, because I think they kind of elucidate that picture. And some other time, maybe later today, I can tell you about observational searches. I'm not going to do that now. I will say, as a little pitch for my student David, who is defending his thesis in 2 weeks, is that all of what I've talked about, we've done also for retrograde accretion disks. And so this is a cool movie he made. This is what we've been looking at prograde. Over here is the retrograde case, where the disk is going the opposite way as the binary. If you zoom in, there's some really different dynamics going on here, including this wild bridge that sometimes goes unstable, flares. There's all kinds of crazy things. And so this is also something David visited here and worked with Andrew on this. And there's some really cool stuff we're doing with that as well. So lots of dynamics in this problem, lots of physics that hasn't even been added yet. And I'm going to end there. Thank you all. I'll put a summary up, but I don't know how to do it, so I'll just
You could stare at that all day.
Yeah.
There were lots of questions. Any